Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. We are continuing with our alkyl halide series. We are now in video number 11 and this is titled The Competition Between E1 versus E2, SN1 versus SN2 and Elimination versus Substitution. Now in the previous videos we have done all mechanisms of elimination, all mechanisms of substitution. And it's time that we understood what is the competition between various elimination reactions, namely E1, E2. What are the factors that drive SN1 and SN2? And how do we know when to use elimination and when to use substitution? So that is coming up on this video now. So the first thing that we will be doing is competition between E1 versus E2. Now, as you may know, primary alkyl halides, if you give them a choice of elimination, they will prefer to go E2 rather than E1, mainly because they cannot form a carbocation. If you remember, E1 forms a carbocation, whereas in E2, there is an elimination in such that the proton and the leaving group leave simultaneously. So there is nothing wrong with a primary going through an E2 because it's not, it simply is not difficult. But E1 is a problem because it can't form a carbocation. So preferably a primary would go for E2. So primary RX prefers E2 as carbocation formation is difficult. Now if you were to look at secondary and tertiary, then definitely secondary and tertiary would both go for E1 and E2. E1 because the carbocation formation is a little bit easier. And in E2, the transition state is stabilized by hyperconjugation. Now, I hope you remember all of this. If you don't, please make sure you go through E1 video, E2 video, SN1, SN2 video. Once all these videos are finished, I'll drop the links of all the videos in all the videos so that you will be able to go through the previous ones before you jump into this one. So remember, secondary and tertiary can form a carbocation, at least relatively easier compared to a primary. But they also prefer E2 because if you remember in E2 we discussed the transition state formed during E2 is actually stabilized by hyperconjugation of the CH3 groups on carbon. Therefore, the secondary and tertiary can also undergo E2. So they can undergo E1 as well as undergo E2. Now E2 is favored by a strong base while E1 is favored by a weak base. Now again, this is important for you to understand. You see, in E2, it is the base that starts the reaction. It takes the proton and that drives the leaving group to go. So the proton has to be strong enough. For E1, actually, it doesn't really matter what kind of proton you have because once a carbocation is formed, its alpha hydrogens are already acidic due to hyperconjugation. So even a weak base will do. So it's not that E1 prefers a weak base in that sense. The reason it doesn't like strong base is because strong base will also have a tendency to do E2. Whereas a weak base cannot do E2 at all because it cannot pull the proton, at least not fast. And therefore, for E2 to happen, you would have a strong base. For E1 to happen, you will have a weak base. And then E2 is favored by a polar aprotic solvent, while E1 is preferred by a polar protic solvent. And that's because the E1 occurs when either water is a solvent or co-solvent. Because as you know, that a polar protic solvent would be able to solvate both the cation and the anion, and therefore the formation of carbocation is easier. But when there is a polar aprotic solvent, it is difficult to form a carbocation because in that case, the absence of proton will not solvate the anion and you won't get that much energy released. So E2, which is a non-carbocation mechanism, would go for polar aprotic, whereas the other one would go for polar protic. As far as non-polar is concerned, non-polar cannot support anything. In fact, non-polar is kind of a dormant solvent. Non-polar solvents like CCl4 or benzene, which have zero dipole moment, they will only allow free radical mechanisms to happen and not ionic mechanisms. Now, if you want to look at rate of E1 and versus E2, remember tertiary is good at both E1 and E2, while primary is the least favorite in both. Least favorite in E2 because it doesn't have any hyperconjugation to stabilize the transition state path, and not even because carbocation formation is difficult. Now let's look at the competition between SN1 and SN2. Now primary RX prefers SN2. Now as you can see, SN2 is parallel to E2. There is no carbocation formation. So SN2 is preferred by primary RX. Tertiary would prefer SN1 as carbocation formation is easy. And unlike the elimination where tertiary preferred both E1 and E2, here tertiary will only prefer SN1 because in SN2 steric hindrance comes into play. And that steric hindrance is a problem, and tertiary cannot undergo SN2 because of that factor. And then secondary would swing between both. Now when it comes to the nature of nucleophiles, strong nucleophiles will favor SN2 while weak favor SN1. Now why is this? That's because in SN2 there is a direct competition between the nucleophile and the leaving group. So the nucleophile has to be stronger at least than the leaving group. But in SN1, the leaving group is already left and then the nucleophile attacks. So nucleophile doesn't mind coming in place. A weak nucleophile can come in place of a strong one. And I've already discussed this in the case of SN1, how this helps us remove a good nucleophile and bring in a weak one. So SN1, you can have a weak nucleophile. Now the reason you don't like a strong nucleophile there is because it will have some tendency to do SN2. But if you're taking a tertiary substrate, it doesn't really matter whether you have a strong nucleophile or a weak nucleophile. Both will do SN1 because the substrate is tertiary. And just like elimination, the polar protic would prefer SN1. And the rate of SN1 would be tertiary, secondary, primary. And the rate of SN2 would be the reverse. So now let's go for the competition between substitution and elimination. So first let's look at the solvent. Remember, the presence of H2O is very important for any mechanism involving a carbocation. So if H2O is either a solvent or a co-solvent, then if there is substitution, it will be SN1. If there is elimination, there will be E1. So H2O is highly polar protic and favors ionization and promotes both SN1 and E1. So if H2O is a solvent or a co-solvent, it will undergo SN1 or E1. But if there is no water in the reaction, it may be assumed to take place by SN2 or E2. Even things like ethanol, methanol, and acetic acid, though they are polar protic, they cannot ionize the substrate that easily. And therefore, they would still prefer the SN2, E2 type mechanism. So let's take a couple of examples. Again, look at the situation. I'll give you the example. Make the product on your own, write the mechanism, and then you can compare. So I have a tertiary substrate and I have water as the reagent. Now you need to make the product and write the mechanism. So now if you're wondering whether I should be doing substitution or elimination, in general, whenever heat is supplied, elimination would be easier. And substitution will be relatively lower in that case because elimination would sort of overtake substitution. So here it will be substitution, and since it is tertiary, it should be. Okay, I'll give you some more examples. I think I'm going to give you all the examples together. Note down these examples and pause the video. Then once the examples are over, I'll tell you when they are over. And so here are at least 6 of them. Now make the product in each, write the respective mechanism, and then play the video back. So the first one, as I already mentioned, is tertiary. There is no heat involved, so it will be substitution, and tertiary will only undergo SN1. So it will form the alcohol, tertiary alcohol, and it will be SN1. What do you think will happen next? See, there is a delta there. This means there will be elimination. Now, what does a tertiary do? Tertiary can do both SN2 and SN1. But what is a solvent? H2O, polar protic. And since it can go, I meant even and E2, not SN1, SN2. H2O delta would mean elimination, even or E2. And since it is water, it will be even because, well, it can form a carbocation. In the next one, there is secondary. Remember, it can undergo almost any mechanism, but there is no heat. So it will be substitution. So it will be either SN1 or SN2. But water promotes the formation of carbocation. It will be SN1. Again, secondary, but this time I'm heating it. So what do you think will happen? Elimination. What kind of an elimination? Secondary can show both even and E2. But H2O will lead to the formation of carbocation. So it will be even. And moreover, H2O is a weak base. Next one, MEOH. What do you think will happen? No heat. Substitution. Which one? SN1, SN2. MEOH is not water. So it will only undergo SN2. The next one, again, no water. So no question of two mechanism. So it is going to be elimination, and therefore this will be even, but it will be slow because the solvent which is going to act as a base itself is a weak base. Next, we have one more example. I get 50% aqueous MEOH, and I get 50% aqueous MEOH here. So obviously the moment there is water, it will lead to the one mechanism, carbocation. And this will go, the first one, there is no heat, it will be SN1. And the second one, heat, there will be E1. The next thing to take care is the temperature. Now, increase of temperature increases the rate of both elimination and substitution, but the rate of elimination increases more rapidly because you are eliminating a molecule that needs heat. When it comes to base nucleophile, now there are several categories. Strong nucleophiles with weak basic character. Try and understand. Strong nucleophiles. The nucleophiles are strong, but their basic nature is weak. So since the nucleophiles are strong, they would prefer to more act as a nucleophile than as a base. So what do you think they will prefer? The strong nucleophiles would prefer, since they're nucleophiles, they would prefer substitution over elimination. And what kind of a substitution? SN2. SN2 is the one that needs a strong nucleophile. So strong nucleophiles with weak basic character, such as HS minus, I minus, Cl minus, and they are strong nucleophiles because their electron cloud can be polarized. And if you remember, if you've seen the SN2 video, I told you, it is a polarization of these electron clouds that leads to SN2. So these are strong nucleophiles, but since they are big ones, they are not strong bases, and therefore they will prefer substitution over elimination. And that will be SN2. If they are strong nucleophiles as well as strong base, they can do both substitution and elimination. And since they are strong, in substitution they will do SN2, and in elimination they will do E2. Now, if a highly acidic H is present, obviously E2 will dominate over SN2. But weak nucleophiles with weak basic character can only do the one mechanisms, that is SN1 and SN2, like alcohol, water, etc. Now, sometimes there are bulky bases, and they are actually strong bases, but since they are bulky, they cannot act as good nucleophiles. So they will purely show elimination. And since they are strong bases, they will show E2. So suppose you have bases like tertiary butoxide, ET3N, Me3N, DBU and DBN. I'll show you what they are. And they are hindered ones, and they will only prefer elimination over substitution. And since they are strong base, they will prefer E2. So this is your DBU, 1,8-diaza bicyclo 540 undex7-ene, and this is DBN. You don't really have to remember all of this, but you need to know that they are hindered bases. So what do you think will happen here? This is something, H2O, heat, you have to make the product. So what do you think will happen? Now first you look at the fact that it is primary, right? But remember, it's a hindered primary. Even though it's a primary, it's a neopentyl halide. And therefore, it cannot undergo the two types of mechanisms, even though they are primary. And since there is a heat, it should be elimination, even or E2. Now, H2O will say E1. And moreover, for even otherwise, E2 cannot happen because the carbon that is adjacent to the leaving group doesn't have any, any H. So this carbon doesn't have any H in it. So even if it wants, it cannot do E2, but it will not do E2 because water is present. So it will be E1. Let's look at the next one. What do you think will happen here? Well, here the hindrance is not as much, and there is also a possibility of an H that is adjacent to the leaving group. This H is present. So here again you have elimination because there is heat, E1 or E2, and E2 will dominate over E1. As it is ethanol, it's not going to give you carbocation. So ammonia and its alkyl derivatives can all be considered as strong nucleophiles with strong basic character. So ammonia and its alkyl derivatives are considered as strong nucleophiles as well as strong bases. So the next point is substrate. Substrate influences this. How? Primary will prefer only E2 and SN2. So if you don't heat it, it will be SN2. And if you heat it and introduce a strong base, well, it's perfectly E2. So don't heat it, it is SN2. Heat it, it is E2. Now tertiary will prefer E1, E2 as well as SN1. So if you have a tertiary and you have ETOH, now here you get a carbocation and you get, remember there is no heat. I have ethanol here, there is no heat here. So if there is no heat here, it is only going to substitute, and it will be substituting by SN1 because remember, it cannot do SN2 because tertiary is going to hinder. Now you may say there is no water, but those are the concessions we have to make. So this is SN1. And what if I give you this situation? What do you think will happen? Now tertiary means E1, E2, SN1, right? Heat, SN1 is removed, only E1 and E2. Now you have a strong base. Strong base will prefer E2. Try the next one. What do you think will happen here? Heating, elimination, E1, E2. And you get this product, that's not a problem. But we need to know what the mechanism is. Is it E1 or is it E2? Now remember, it's a tertiary. And but the base, as you can see, is not strong enough. So despite not being a highly polar protic, it will still make it E1 because the base is not strong enough for E2. But if there is no heat involved, it will be substitution and purely it will be SN1 because SN2 cannot happen on a tertiary. So you need to understand where which parameter plays an important role. So go through these examples once again and you will be able to figure out how to deal with that. Secondary, strong base. So what do you think will happen? Well, secondary with strong base should give you E2 at high temperature. So it will give you E2 at high temperature because strong base will take care of that and secondary can undergo E2. If it is a strong nucleophile instead, it will undergo SN1 or SN2. At low temperature, it will undergo SN2. Because remember, nucleophile is strong and the strong nucleophile prefers SN2. If I have a weak base, since I'm writing it as a base, it has to be elimination, it will be E1 and at high temperature. And if it is a weak nucleophile, it will be SN1 at low temperature. So what do you think will happen in this case? I'll get this because there is no heat involved. But what is the mechanism? Purely SN2. Why? Because the base is strong, the nucleophile is strong. What about this one? Suppose I heat it. Now what do we do? Well, it is secondary. I can make it happen even in E2, but it will prefer E2 because the base is strong, MEO minus. This guy, this MEO minus is going to act as a strong base. So it will be E2. What about this one? Now here, there is no heat, yet it's a substitution. It's not SN2, it is E2. And let me explain this. See, what happens is that when you have ETO minus in ETOH, ETOH solvates ETO minus sufficient enough for it to become a little bulky. So because it is bulky, it will not do substitution that easily. Okay. So because it is bulky, it will not do substitution easily. But it is not going to be bulky enough to do even CB. Or it will not be, not even CB, I meant Hoffman elimination. So it is bulky enough not to do substitution, but not bulky enough to make a Hoffman product. So what actually happens is, here, this is because ETO minus gets solvated by ETOH. This solvated ethoxide ion becomes bulky and therefore tends to behave more as a base, but not bulky enough to give a Hoffman product. So now tell me what will happen. Suppose I have ethoxide in ether. There is no solvation there. So there is no elimination. There is an act as a nucleophile. It will be SN2. What about this if I only have water? You guessed it right. SN1, no heat. What do you think if I have water and heat in this case? Now water will be E1 or SN1. Heat means E1. So now you got to identify the mechanism and form the correct product for each. So you have this one with H2O and heat. Pause and make the product. So obviously H2O means SN1 E1. Heat means E1. So it will eliminate and give you E1. Okay, secondary coming up. MEO minus MEOH. There is no heat. Substitution. Strong nucleophile SN2. So the next one is this. It's again, if you notice, it's a primary thing. I minus is a good nucleophile. It will do SN2. No heat involved. Number 4, I have I minus with water, and despite water, it will still undergo SN2 because it's a strong nucleophile and a primary substrate. And I have this one, and I add a hindered base. Now, even though I'm not going to write heat, it is still elimination because hindered bases cannot be good nucleophiles. And it will always give the Hoffman product. So E2 with Hoffman product. Next one, I use ethoxide and ETOH. Again, I don't write heat, but you know that ETO minus is solvated by ETOH, making it again bulky enough to act as a base and not as a nucleophile, but not give you a Hoffman product, give you these sets of product. So in this one, you have Ki in aqueous THF. Aqueous, the moment you see aqueous, it is SN1 or E1, no heat SN1, and therefore you get an I here. This one with ethoxide and ETOH, again you know it will not act as a nucleophile, it will only act as a base, and you get elimination, E2. And the next one, I have a hindered base, Hoffman product, elimination only, E2. Couple of more examples. So I have hydroxide and water, no heat, so substitution. Water SN1, Well, here you have an interesting one. Alcoholic KOH and heat. Obviously elimination. But what is the product formed? Product is simple. Now this Cl, if it wants to go with this H, but this H is also on top, because this Cl is the bottom, the H will be on top. And here the H will be bottom. So this Cl and H cannot go because you need anti-coplanar for elimination. This Cl H cannot go. So this Cl and H, this H will go, this Cl and this H will go. And you get a conjugated product. The next one, again, neopentyl halide, aqueous KCN, no heat, substitution, but it will undergo SN1 because of the hindered part. And if it undergoes SN1, it will form a carbocation, they will rearrange, and eventually the CN comes here. And the next one is this, bad living group, alcoholic KOH, remember even CB. So you get the Hofmann product. But in the same place, I have a bromine, alcoholic KOH. It will perfectly undergo SN2 because it's alcoholic KOH, and therefore it is E2. If you look at this one, this is a tertiary one, and I have a strong base and heat. So tertiary, strong base, heat. What do you think? E2. You have a tertiary. You have MEO minus MEH, no heat, so it will be substitution. And since it cannot undergo SN2 because of the hindrance, it will go SN1. And a few more. Hindered. You get a tertiary butoxide, which is also hindered. You get a Hofmann product, E2. You get a tertiary here. With tertiary butoxide, again, E2 with Hofmann product. And the last example is MEO minus MEOH and heat. Heat is elimination, even E2. Tertiary can undergo both, even E2. No water, so E2. And you get the Sidzer product. And that is the end of this particular video. So I hope you sort of got what I meant to describe in this video. The substitution versus elimination, even versus E2, SN1 and versus SN2. Go through this video as many times as you want and try and understand every one of the concepts that I taught here. Very, very important video. And give a like if you like this video. And if you want to see more videos of chemistry, organic, physical, inorganic, over a period of time, I'll be making all of them. So subscribe and hit the bell icon to make sure that you get notified on time whenever a video is uploaded. With that, Kalyan Kumar signing off. Have a nice day and be safe.